and thanks for having me, and thanks for coming here. So tonight I'm gonna tell you a little bit about what NVIDIA has been up to in terms of building up our internal AI infrastructure to support massive scale projects like self-driving cars. We're also, busy and involved supporting other internal projects, but to me, what we're doing for self-driving cars is really unique and worth talking about because of the scale involved and the challenges we have in developing these systems. My name is Clément Farabet. I've been with NVIDIA for almost 2 years now, and I'm a VP of AI infrastructure there. And so this project I'm going to walk you through is really one of the biggest things we're focusing on today in my team. So before I dive in and start telling you about what we're building, it's worth kind of like recapping where NVIDIA is at in terms of self-driving car software and what our strategy is. As you guys know, NVIDIA is historically a GPU company. It's a company that's been selling graphics cards and then building software to enable those graphics cards to be used seamlessly into video games. And then a few years back, it started building this great piece of software called CUDA. And since then, NVIDIA GPUs ended up being used in all sorts of high-performance computing applications, one of them being deep learning. And deep learning has been really tapping into the GPU power massively over the past 6-7 years. In fact, around 2010-11, folks working in deep learning labs all started tapping into GPUs, and that's really how we started getting amazing results. So I remember back in the days I was doing my PhD with Yann LeCun at NYU, and the GPU was literally the thing that took us from scrappy demos to things that actually started to work. And so CUDA has been there all along. What we're doing with Drive is kind of like one of these big verticals we're attacking, where the idea is that we're building the full stack from an SoC that's super high performance. It's a family of chips that go into the car and that we're selling to OEMs, car companies, and so on. We call that Drive AGX. There's a family of chips. The most high-performance one we have on the market today is called Pegasus. It's literally packing something like 300 tera-ops of compute power in that SoC. And so you can imagine the amount of stuff you can actually pack into that car. And the reason we're doing that and the reason the entire car industry is moving in that direction is that we believe that the future of cars is going to be entirely software-defined. In fact, in the previous talk, we had a quick example of the Ford pickup, which uses something like 150 million lines of code, was it? Some pretty large number. And believe me, a Ford pickup truck is not a self-driving car yet. And so where we're going is we want to enable the entire industry to essentially go put that in their car and program this whole thing and build up their entire AI stack all the way to high-level planning functions, mapping functions, and so on. So why is this challenging? So it turns out that to drive a car autonomously, you actually need to implement more like north of 20-25 unique functions that are essentially mapping everything that surrounds the car into some kind of internal representation that you can use to safely locate the car and then actuate the car in any environment. So these functions include anything from safely detecting objects around the car, like trucks, cars, and pedestrians, and so on, to things like estimating the distance of all the objects around you, so actually mapping them in some kind of like 3D representation, to things like building an understanding of path, and that goes well beyond just recognizing lanes. It's really about estimating all the possible paths that can be driven and taken by the ego car. And so these functions are incredibly complex. But what really makes them complex, I think, is two things. One of them is the diversity of environments and scenarios that you have to actually get them to work in. So it's not enough to train one of these models and get them to kind of like do the right thing on the highway on 101. You actually have to go get them to work in literally any environment. All types of roads, all types of weather conditions, night conditions, when it's raining, when it's foggy, or when it's like smoggy like it is today. So it's like all these weird types of light conditions, and whatever you do, there's always going to be this tail of things that you haven't seen before. So it's really a super tough, I think it's one of the most challenging machine learning I've had to work with. And I think the main reason really is that, for many machine learning problems, we have for most products, it's kind of okay to deploy something that's not perfect. anything that kind of beats a human written baseline is enough to ship. Whereas self-driving cars has this kind of like binary step function of you have to reach that level of quality before you can actually put it on the road. And it gets me to my next point, which is that it's really all about testing. So for most problems that we get to work with in machine learning, training data sets is really the big problem. Test data sets are typically smaller. For self-driving cars, it's kind of the opposite. The scale of testing we're talking about is really daunting, and the reason for that is that the industry is basically wants to be able to prove that all the functions we implement beat human performance. And we have statistics on how many accidents and issues human drivers cause on real-world data, and they're typically pretty good. And so this basically leads to these types of numbers. We think that we're going to have to essentially validate every single neural network, every single function we implement on millions of miles of real data. So real data that we're going to go collect on the road that covers all these types of scenarios, and we're going to have to validate these networks at that scale. And then we think we're going to have to go all the way to billions of simulated miles so that we can extend all the combinatorial all the combinations of things that we think we're going to be observing in the real world. So the scale is really daunting, and I think that's the main point I want to make here. The red curve is kind of showing our roadmap in terms of like failures and how far we want to push these things. And the green curve is showing how much data we're collecting to support this roadmap. And so, just to make this very concrete, this is where we are today in our endeavor towards building these self-driving car modules. The first column tells you about the type of data we're dealing with. So we have a fairly rich rig with 12 cameras mounted all around the car, radars, multiple radars, lidars on the car as well. And this rig is mounted on roughly 30 cars that we have driving worldwide. And we're roughly ingesting something that peaks to a petabyte of raw data a week. And so for folks working in large-scale web companies, this doesn't sound like a crazy high number. But the thing that's really tricky about this is that all of it is actually used at every time by our team. So today we have curated roughly 15 petabytes of training and test data, and that's actually our active set that we use to do machine learning on a daily basis. And that's what really makes it complicated. And coming back to the last slide, that's where we are today, and it's really a scary exponential curve where we're gonna have to cover so much more basically. The second column shows you the augmentation we have to do on this data. One thing that's a little bit tricky about self-driving cars is that there's a lot of things we can get from the driver. Like some of our networks actually predict the path that need to be taken, and they predict the roads based solely on imitating the drivers that collect the data. But some of these things I showed before can't be done like that. They actually need labeling. So we employ roughly 1,500 labelers full-time, work in 2 shifts, and it's a fairly big, just maintaining this thing and feeding them with the right data and making this efficient is actually a big endeavor as well. So we're roughly collecting, labeling 20 million objects a month. And that's covering a few, like 20 unique models, 50 labeling tasks. And I'll say more about this. The act of selecting the right data for training and testing is really important. And third is the compute and storage. So once you have all of this, it's critical that you actually feed this into a cluster to train your models and test them at scale. So here we're talking about roughly 4,000 GPUs in a cluster. That's 500 petaflops of compute, and our goal is to essentially build infrastructure to support the development of all these models and sustain compute on that cluster. So I think at that scale, there's a bunch of fundamental challenges. One of them is the fact that I think that as an industry, getting AI and machine learning into products is really bottlenecked by a few things. One of them is our ability to develop the right data sets. Whether it's for training or for testing, different industries have different challenges. For self-driving cars, it's incredibly challenging because you just can't have access to the true distribution. The real data is basically incredibly diverse and scattered all over the world. We don't really have access to the target distribution of where the cars are going to drive ultimately. So that alone is a huge challenge. Once you collect the raw data, organizing them into data sets and making that available to the team is also really challenging because of the scale. And then things like running the right experiments, instrumenting everything so that your whole methodology is metrics, KPI driven, really important, and ultimately automation, and I'll say more about that. And our belief is that if we solve these problems and we have great infrastructure to organize all this work to develop these models at scale, then we move into a world where adding more compute into this cluster is literally turning into more rapid progress, which is not really true if you don't have enough infrastructure, because you're typically bottlenecked on the number of data scientists in your team. So back almost 2 years ago, we essentially decided to start this project that we call Maglev. You can think of it as our NVIDIA's internal AI platform to support our industry-grade AI needs. And this is really being driven by the scale and challenges of organizing our data and workflows and methodology for heavy. So let me get into it and start telling you about what this platform is doing. At a very high level, we're trying to solve three big high-level problems. The first one is dataset lifecycle management. So from the moment the data hits the data center to when it starts being consumed by the team, we want to have a great methodology to essentially index everything and make it searchable and make it queryable for all sorts of downstream tasks. And I'll say more about that. The second pillar is ML pipeline automation. We want to have the ability to essentially describe our end-to-end machine learning pipelines and then schedule them on the cluster and have them reproducible. And I'll say more about that as well. And at the end of the whole pipeline, we're interested in model analytics and insights and basically helping the team understand what action to take next to keep improving their models. So focusing on the first pillar, so dataset lifecycle management is, I think, probably one of our most challenging problems. Again, because of the scale of the data we're dealing with and the variety of access patterns that the team wants to be able to run. So we've kind of built two worlds. The first one in green is essentially our large-scale, petabyte scale management system, and it's a pipeline where we're essentially writing a lot of the data into Parquet, and then providing access to the team through multiple interfaces. So we're using Presto, Spark, Hive, and then exposing multiple front ends to essentially let the team compose data sets and query arbitrary data sets dynamically. And on the right side, we've basically invested a lot of effort into building Python-side clients to essentially enable the folks developing the models to rapidly compose and assemble data sets dynamically and let them sample from multiple sources and compose data sets at runtime. And the challenge we're trying to solve here is that companies with established large-scale infrastructure, with great MapReduce infrastructure, typically tend to push a lot of the work on the left side. Essentially, any dataset creation is going to be a big MapReduce job. On our side, we've tried to split that into two, do less things on the MapReduce side of things, and enable the client-side consumers to actually do much more at runtime. The second thing I want to show you is the actual how we've kind of organized this whole thing. So the whole platform we've built is based on Kubernetes. Kubernetes lets us essentially scale and manage all the services we have. So today we're running roughly 20 microservices, doing all sorts of things from managing the workflows we run on the cluster to tracking our experiments, the data sets we're consuming. And all these things are kind of seamlessly running on top of Kubernetes. This lets us do one thing that's really interesting. We went for a hybrid approach where a lot of our services and data management is actually entirely hosted on AWS, which is really great because we can scale some of these services elastically. So a lot of the ETL we have to do and the data we ingest needs to be adjusted dynamically. Sometimes we're going to need a few thousand nodes, sometimes just a few hundred. So we can kind of elastically scale all of that. But then at some point, the workflows themselves run exclusively on our on-premise cluster. We've packed up 4,000 GPUs so far, and our goal is to basically keep these guys busy with training and testing our models. I'll skip that. So this view is really interesting to me. I think a lot of what we're trying to achieve with this infrastructure is to essentially start reconciling production engineering, DevOps, and machine learning developers. These two folks typically, don't interact much. The machine learning developers tend to work in a world where they write a lot of Python code. They deal with fairly small-scale data sets, and they move very fast, and are very focused on iterating on new and novel approaches to algorithms and how they're solving the problem. Whereas on the kind of like DevOps and production engineering side of things, the whole goal is to automate everything, scale up the work that's been done to really large-scale problems. And so what we've done here is essentially a world in which we can programmatically describe workflows running on Kubernetes on our cluster. The machine developers in our teams typically describe these workflows and run them in ad hoc ways, and they do a lot of science like that. The workflows let them do things like hyper-optimization, schedule multiple jobs at scale, compare results of multiple machine learning approaches and techniques, and so on. But then the beauty is that once the workflows are finalized, we're basically versioning them. And then we have a way to essentially schedule workflows straight out of Git so that the whole end-to-end pipeline is reproducible and can be cron-scheduled. So ultimately, that's where we want to be. We want to be in a place where research and R&D on the models is decoupled from production, but using the same code base. And so the production engineers can essentially schedule those things, and the output of that is trained models, versioned data sets, metrics associated to each models, and it gives us a really healthy way to track everything that's produced and deployed in production. The side effect of that is so automation is really the top goal. The side effect is also traceability. And I want to draw a little parallel here. For the past 20 years in traditional software development, we've really learned to manage traditional software the right way. We use versioning systems like Git to trace and everything we do. We rely on deterministic compilers so that any code versioned in Git can be turned into an executable in a deterministic way. Machine learning is not there at all. Machine learning is still very wild, but I believe we need to get to the same level. And I like to draw an analogy where you can think of machine learning where the data we use is basically analogous to source code. And the algorithm itself, like deep learning or machine learning, is basically a compiler. And it turns this data into some kind of predictor that you deploy in production. And so what we're trying to do here is get to a point where we have the same level of sanity, where every data set is versioned, tracked, and then our deep learning and machine learning stack is entirely deterministic so that we can compile that data into our predictors. And so it's a massive effort because the industry is not standardized on any of this yet. And we think we have a lot of things to contribute to that. One more view, which is perhaps the most concrete I have, is showing you the two big clusters we're running. On the top side, it's our cloud side of things running on AWS today. At the bottom, it's our on-premise cluster with 4,000 GPUs. And it's really showing you the pipeline of how we deal with data. So we're ingesting a fairly large amount of data. It ends up being stored in that data lake. And then one of the main type of workflow we're running is what we call data selection, which is really about applying pre-trained neural networks to go do inference on data and select which data needs to be labeled the most. So one of the things you observe when you start building applied systems with machine learning is that at some point your performance starts plateauing. And the reason it plateaus is that all the new data you sample and label, you're actually classifying it perfectly well. So one way to think about that is, if you have a model that has 99% accuracy on random data, it means that 99% of all the data you get is already well classified, 99% of it. So there's just 1% of it that's really wrong. And so if you keep labeling data randomly, you're basically wasting your time 99% of the time. And so this is basically active learning. active learning is really this body of research aimed at biasing the data that you decide to label to keep growing your training sets. And so to us, data selection is really critical, because very rapidly you get to a point where your models work 99.99% of the time, and it's all going to be about finding the new edge cases in that whole pile of data we keep collecting. And then the second big job is testing. So we're continually increasing the size of these test data sets so that they cover more and more scenarios. And we want to be able to test any model we train at these ridiculously large scales. And then, of course, training, which people are typically more familiar with. One last thing on that infrastructure we're building, we've put a lot of effort into the hardware layer as well. And the reason for that is we essentially spend our days training and testing these models and moving data around. And so it's really critical that we don't have any bottlenecks across this whole pipeline. Our entire platform running on top of Kubernetes is built against object storage. So all our data sets are stored on object, and typically on AWS S3. And then what we've done is we've got a replica of S3 locally on-premise, which is using the same API, so it's all S3 based. And then we've kind of like racked up our systems in a way that's hybrid, where half the racks are DGX systems. So DGXs are these big fat nodes with 8 Volta GPUs. So these are monsters. And we've packed 9 of them per rack, and then 12 CPU nodes. And that gives you roughly something like 1 petabyte of distributed storage per rack, feeding into 9 DGXs. And that's 9 times 8, so 72 GPUs per rack. So it's a super high density model where data can be locally cached. We use object APIs all the way. So it's kind of like a 3-tiered system. All the data is safely stored on S3, and that gives us replication worldwide. We can ingest in different continents. But then the on-premise gives us the local caching, and then ultimately next to the compute. So it's a cool design, and we're starting to recommend that design to our customers so that they can deploy high-performance compute clusters. All right, I'll stop there for maglev. I want to move on to another project, which is mildly related but largely orthogonal. So this is something else that we've started in our team a while back. And we actually just launched this around a month ago now. So it's all new. We're super excited about this. You can check it out at rapids.ai. So the project is basically an open source Python first and GPU first data science ecosystem of libraries. And conceptually, the way we've organized and built this whole thing is quite simple. If you guys are familiar with Spark, what Spark did for MapReduce and Hadoop was essentially starting to move away from writing data in and out of disks and starting to do everything in CPU memory. What we're trying to do here is essentially push this a little bit further and push everything into GPU memory. So the idea is that we're standardizing around Apache Arrow for the format we're using for all the data we're dealing with. And then our goal is to basically load everything up into GPU memory and then have the data never leave GPU memory. And then build and provide all sorts of interconnects into multiple libraries. One of them is called cuDF. You can think of cuDF as a pandas clone. So pandas is basically a library to create data frames and manipulate data sets and do joins and group bys and sort data sets and so on. This lets you do the same exact thing entirely based on CUDA in GPU memory. Then QML is a collection of machine learning primitives from k-means to XGBoost. We're supporting XGBoost, so GBDT, decision forest, and so on. Our end goal here is to support the full scikit-learn API and XGBoost as well. We're way advanced on XGBoost. We still have some work to do around scikit-learn. And then kugraph is a whole bunch of primitives to manipulate graphs efficiently in GPU memory again. And then the other cool thing we're doing is that we're starting to build bridges into deep learning. This is all new, starting to basically connect this format to libraries like PyTorch, so that once you've loaded up your data sets into memory, you can do some feature engineering, some quantization, and then ultimately pipe your data into a deep learning solver. So we're super excited about this. One thing that's really great is that when it's open source, We're trying to stick to existing Python APIs to make the onboarding on this really seamless. And the latest thing we've started now is we've started integration into Spark as well. Where the goal is going to be to make this also seamlessly available through the JNI in Spark, so that you can schedule the same types of jobs through Spark. One thing that's really great is looking at the end-to-end benchmarks. So it used to be that traditional ML was really hard to speed up on GPUs because compared to deep learning, you have a lot less dense, matrix multiplies and compute, and so it's kind of like it's harder to optimize. And one of the challenges with these types of workflows in data science is that you spend a lot of time doing I/O and feature engineering, and ML is typically just one aspect of the whole pipeline. But because we're taking a holistic approach and we're loading up everything into memory, doing even CSV decoding and Parquet decoding is going to be done once it's in GPU memory. You basically don't waste time on I/O. So you load things up once, and then you're basically unbounded. And the bandwidth between the GPU memory and the GPU is incredibly higher than the bandwidth between CPU and CPU memory. So really cool stuff. The coolest result here is, so DGX2 is the craziest system that NVIDIA is building. It's 16 GPUs packed in one node, so an incredible amount of compute power. The craziest thing about DGX2 is that it has 0.5 terabyte of GPU RAM in one node. So you can start doing a lot of things without having to distribute anything. Realistically though, systems like DGX1 with, I think, 128 gigs of RAM are going to be more common. And what we've done here is basically scaling out the whole data processing and then machine learning through Dask to distribute the load. Again, in terms of development, the whole project is open source. So we've been working with quite a few partners on that, particularly the folks from Anaconda, Blazing DB, like very tight collaboration with them. InRia and Scikit-learn, Databricks on the Spark side, and I'm trying to find, and Ursa Labs, who is basically leading the RO2 definition. And so we're working very closely with Wes McKinney, who came up with RO in the first place, and really trying to align on that so that everything we do is centered around that. All right, and obviously, my team is hiring very intensely, so if you guys are interested in any type of job at the intersection of high-performance compute, GPU, and big data, either for internal applications like what we're doing for self-driving cars, or these types of open-source projects we're building through Rapids, feel free to reach out to me, my Twitter handle. All right.
Thank you very much for an information-dense presentation. I'm sure we have time for questions, and I'm sure there are some.
Yeah.
So what's the deployment model? Talking about like the infrastructure, the previous part in MagLab and Drive. What's the deployment model? Are you going to sell it? Are you going to open source it?
Yeah.
Give
So
it free?
So we don't. So right now this is our internal infrastructure. And so today we're focusing on enabling all our internal teams to build these new stacks, including self-driving cars, but we don't have a go-to-market plan. But as soon as we do, it'll be public, and so. Yeah.
So you mentioned, so in the diagram you showed that like density factor, and so like typically what happens in those kind of cases, like with the kind of working set size that you mentioned, and you also mentioned that you were doing object store. Typically, you swap the torque or the ore on the racks. Like how are you like? If you have any like cache locality like on the nodes when you do them, because you can't keep the whole working set, even though you have like 500 gigs of RAM in each node, like you can't keep the whole working set in GPU memory. You don't have enough machines. So like how?
Yeah,
could you talk about locality and what networking for you in the networking substrate?
Yeah, it's a great question. So it's a tiered approach where, so in each DGX here, we have 7 terabytes of SSD per DGX. And so this typically gets you to, like there's a whole bunch of like training data sets that typically fit in that. But then, a lot of our test sets are actually significantly larger than that. And so then we start doing everything. Everything is mapped and not even cached locally, but it's typically cached in the upper part of the rack, which holds 1 petabyte. And so 1 petabyte is pretty much enough for anything we need to do at that point. But yeah.
So you basically so you memory map the files on the CPU on the CPU nodes.
Exactly.
And use those as for I guess predefined sets, and you kind of then
Exactly. Yeah. Yeah.
That's fine.
And the infrastructure we've built on top, one of the services we have running on Kubernetes is basically responsible for the data management. And so we have this system to essentially create virtual images so that the active set that's going to fit into a job is predefined. So it's not completely open-ended, otherwise very hard to manage. Yeah. Yeah.
So since you're generating a terabyte of data per week per car, how do you move all that data to your data centers?
Yeah, it's a great question. So it's actually 1 petabyte of data. And it's an incredible challenge, and the only system we've found so far that has enough bandwidth is FedEx. It has shitty latency, but amazing bandwidth. So we literally use FedEx to ship everything. So it's all SSDs. And back in the days, it used to be that the folks at Google Maps, Street View used to do the same thing. Actually, don't know what they do now. But given the volumes of data you're collecting locally in one specific region, you never have enough bandwidth anywhere to actually ingest fast enough. And so we ship data, and we have multiple receiver points worldwide. And then it's basically disk-based, old-school SSD-based. You push the SSD in, and it sucks up everything to the cloud. Yeah.
Anything more? Well, let's
Okay, awesome.
again.
Yeah, thank you so much.